Okay, a new day, a new video in the Advanced SQL course series. Welcome back everyone. It's a new day, so time for new Advanced SQL videos and a deeper dive in some of the constructs that are available to us when we are talking SQL to a database system. For the next few minutes, let's talk about row ordering. Something that your vanilla relational table cannot provide. It's just an unordered bag of rows. But there is a particular SQL clause, the order by clause, which lets us sort the rows in the table. And we could use that for result display. And that's actually a very important use case. So you easily get lost in a sea of rows that is displayed to you in a terminal. And finding or checking whether the result of a query really represents what you expected is much easier if you can order the rows for display. Order the rows for display, then scroll the larger result to easily find what you're looking for. Also, applications may expect that the result of a query is presented to them in a particular order, and the order by clause of SQL can deliver that. We can also use this order by clause to support something that's called positional access. So an access to rows that is not guided by values, by value-based predicates, but by their position in an ordered table. In an ordered table, it may make sense to talk about the first row and the last row, and SQL comes with constructs that lets us do so. Okay, so order by is used as a suffix here to a regular select from where block. And you can see the annotations here that tell us the order of processing of this query. Of course, we first establish row bindings. Then we evaluate predicates to see which bindings of our row variables may pass. Then we evaluate expressions of the select clause to form one of the possible result rows that will be part of the result. And then finally, in the fourth step, we come to the order by clause, which will reorder the resulting rows according to the sorting criteria E1 to En. These are ordered from left to right, so E1 is the most important sorting criterion. Rows are being sorted on the value of expression E1 first, only if there's a tie. Only if E1 evaluates to the same value for two given rows, the sorting criterion E2 is consulted. If E2 reads to a tie, we consult E3 and so on. So it's a lexicographic ordering of rows based on the ordering criteria that you specify, separated by commas here in the order by clause. So the order of the EY of the ordering criteria really makes a difference here. Okay, because we evaluate order by as the very final clause in a select from where query, we can refer to values, to columns, to fields that have already been computed in the select clause. So we will see examples for expressions that compute a particular value here in the select clause at step 3. And then in step 4, we may refer to that value and use it as ordering criterion. Okay, so if that would be our query, you see again here the playground table, our 4-column, 5-row playground table. If we dump all the rows and do not filter anything away, there's no where clause. But if we order stuff according to these order by clauses, then that would be the result that we see. So an ordering by the D column in ascending fashion, which is the default, by the way, will lead to a display like this. So the D values appear in ascending order. All right, there are no ties, so that's actually a very simple ordering that we can see here. And how about the null value? The SQL semantics say that null value is considered to be larger than any other value, unless we specify this optional modifier to this order by clause. in which case null values are being sorted first, are considered the smallest values. That's why we see this row with A5 D null at the beginning of this order display here. We can also order in descending order, and this would be the modifier that we can use in this particular case. So ascending is the default. If we really want to order in a descending fashion, use the modifier descending on a particular ordering criteria. Different ordering criteria may have differing ascending and descending modifiers attached to them. So let's see whether the result what we are seeing is what we expect. Of course, we see all 5 rows, nothing has been filtered away. We order by TB, so by the string value first, but in descending fashion. So the larger string values are being found at the top of the ordered output, and the smaller string values are found at the bottom here. Y is larger than X. We are sorting in descending fashion fits. Some of the rows share their B value. These 2 rows and these 3 rows, they all share their B value. So the B value alone leads to a tie and cannot decide row order. In that case, we will consult the TC column, this ordering criterion. And in the TC column, which will be sorted in ascending fashion, no modifier here, you see that obviously the false value is considered smaller than the true value, so that's the order that has been established here. Also in this X group of 3 rows that have the B value X, the row with the C value false is being considered first, and then these two rows actually are in a tie with respect to ordering criterion TB and TC. In that case, the implementation, our RDBMS implementation, PostgreSQL in this case, is free of choosing any implementation defined order. It's better to not rely on this particular outcome, on this particular order. It might change when the DBMS internally changes its plans on how to evaluate this query. This is some implementation dependent and very unstable order of these 2 last rows. So let's switch over to the interactive terminal and to the live PostgreSQL. This is the first sample query that we had on the slides. Let's see whether we can see the same ordering. Yes. So ascending D values null sorted first. That's fine. Let's comment out this modifier. Commenting out the modifier will sort nulls last, which is also a possible specification, by the way. So that's the default. Nulls are considered to be the largest values in the domain. Evaluating this will sort the row with null at the bottom of this ordered table. We could even uncomment the ascending here because it's the default, and we will see the same display. Okay, so let's repair that example. Okay. Nice. Okay, so this is the second example that you already saw on the slides. Ordering, descending according to B. If there is ties, then the C column is consulted. Falses sort before truths in ascending fashion. This is the tie, and it may very well to lead some other sorting order on the next run. Better not rely on that. Okay. Oh, I've brought another example that shows you that in this order by clause, where I specify the sort criteria, I can actually refer to columns that have been computed. They have been computed by the select clause. The select clause is evaluated conceptually before the order by. So here I'm computing the ratio of the D and A columns and call that column ratio. That could be an ordering criterion. So let's see what comes out of that. This is the ratio of D to A. 20 divided by 4 is 5, that's fine. So if this is our ordering criterion in ascending fashion, the nulls sort last. The division of the null value by 5 leads to null, which as an ordering criterion sorts this row last, and otherwise the ratio defines the sorting order here. As you can see, you can also attach the order by clause to such a literal table created by the values clause. So this is a values clause that specifies rows in order 1, 2, 3. As you recall, because we have no column aliasing here, this column would be created as the column 1. This would be the column 2. I can refer to that in that order by clause, and then these order by this particular column in descending order, and this is what I'm seeing, 3 to 1, exactly what we had expected. Okay. Please be aware that row order is something that's very local. Only because we are using order bys in our queries, we don't switch processing mode from bags to lists. Ordering is really a local thing. Ordering is local to a particular query. The construct of a particular query may rely on row ordering once an order by clause has been attached to a query. But as soon as we leave the context of that particular query, there is no defined row order anymore. I've tried to make that clearer by showing you this particular example, which is using a subquery. So we make use of the compositionality of SQL. This is the from clause of the outer query. It would expect here, it would expect a table that we can iterate over with our row variable t1. Instead of a literal table or a name table, I'm specifying this query, this subquery in parentheses. And as you see, inside this subquery, I'm ordering the rows according to criterion column A. Okay, and all constructs inside this particular subquery, they would be it would be okay for this construct to rely on a defined row order. But outside of this subquery, on the level of this top level query, of this outer query, there is no defined row ordering. This outer query may very well resort the rows and display them in some order that's not compatible with the order locally established inside the subquery. So please be very aware of that. Even if you try this particular query in your Postgres installation now, and you will see that the outer query produces the rows in the order of the subquery, so in A ascending order, that's a pure coincidence. Never rely on that. Plan changes, index changes, any contextual changes inside the database system may lead to varying row orders if you don't use an order by in this particular query. Never rely on such row orders without an explicit order by. Okay, so if row order really is local, what then is could it be good for? What then could it be good for? Of course, on the top level, we could use it for display, for order display. But in such, but also ordering can also have some good sense. Can make some good sense in such subqueries. And what ordering allows is positional access to rows, as I've called it at the very beginning of the video. Normally, with where clauses, for example, we would have value-based access to rows. Please dump all the rows in which the A value is larger than 2. So a value-based criterion, the value of the column A would define whether a particular row is being output here. Okay. In positional row access, we would use the position of a row in its order table to decide whether it should be part of the result. So this really, positional access really only makes sense in the presence of an order table. Positional access will lead to some ambiguous, arbitrary, random results on tables that are not being ordered by an order by clause. And if you ask me, I would say that using such positional access construct in SQL on an unordered table should actually lead to a static error. But okay. So let's see what these positional access constructs in SQL are. They are called offset and limit, and they always go, as I just told you, together with an order by clause. So if this order by clause has established an order of rows in ascending C1 fashion, so rows would be ordered in this table, in this output table, in ascending C1 order, then there is a well-defined row order, and it makes sense, for example, to say offset n, which can be attached as a suffix below the order by clause. Offset n says skip the first n rows in the result, skip the first n rows, and start with row n plus 1 in output. Okay, so in this display, the rows 0 to n minus 1 are skipped. N is the first row that is actually being output. And it makes sense to skip these rows in a defined fashion because we have the order established on column C1. The other construct is a limit construct that says once you've skipped to this nth row, only output m further rows. And whichever m further rows these will be, it's well defined because of the row order established by column C1, by the order by clause. So skip n rows and then dump m rows or fetch m rows of the result, or other rows are discarded. That is positional access, and that makes sense on order tables only. This is a literal integer, so it's not an expression; it's a literal integer that you can attach to such an SQL query. Offset 0, of course, means skip no row but start from the beginning. Limit all means no limits here. Please just dump all of the rows that you've been producing. So offset 0, limit all really is a no op in SQL. There's alternative syntaxes for these limit m clauses, which you can see at the bottom here. Right? Oh, you can hardly see that on the bottom of the slide, but it's not that important. We will always use the offset and limit syntax here. Okay, so let's switch over to the terminal. I think I've got a sample query that displays the behavior of this. Okay, so iterate over all the rows of table T, order them in descending A fashion. So we expect the row with value 5 at the beginning of the output, but we are skipping one row, so that particular row will be skipped. So the first row that we will see will probably be the row with TA equals 4. And we won't see all the 4 residual or remaining rows. We only see 3 of them because of the limit 3 clause. So let's evaluate that and check our hypothesis. Okay, we see 3 rows. If there would be less than 3 rows, we would of course see less than less rows here, but we can dump 3 rows, and the first row has indeed been skipped. So evaluating this subquery without the offset and limit clauses would have led to this result. So we have skipped over this row using the offset clause, and we have discarded this particular row using the limit clause. Okay, very nice. There's another very important use of positional access in SQL, and it's actually not that well known, but we will use it quite frequently in this particular course, and this is the distinct on clause. The distinct on clause always goes together with the order by clause if you want to have some well-defined and some sensible results. Okay, so distinct on allows you to identify one particular row among a group of equivalent rows. So you could pick a representative row among a group of equivalent rows. That's a use case that will occur over and over while we are considering the authoring of SQL clauses. So as you can see, this is the distinct on clause. It goes together with the order by clause here. The processing order is as usual. Actually, we start with a from clause. We will then compute some select expressions, some column expressions here in the select clause, these k expressions over here. Based on these, we can define a row ordering. So everything is normal up to here. And then in the fourth step, the distinct on clause will do its work. And its parameters define what makes up a group of equivalent rows. Okay, from this group, only one row will be picked. Let's make this a bit more concrete. So the order by clause will of course sort the rows in this E1 to EM order. So a number of sorting criteria that you have specified here. Okay. Then, as I told you, all rows that agree on the E1 to E1 values on these first n sorting criteria, they form one group of rows. From this group, we will pick only one particular row. All other rows will be discarded. This one particular row is the representative of its group, of all the rows that agree in these first n sorting criteria. Okay, which row will be picked? Which row will be picked as the representative? Well, this is defined by the remaining sorting criteria. The row that comes first in this particular sorting order, defined by this residual list of sorting criteria, will be the representative. This will be the row that will be picked. Okay, so you see, the distinct on clause only makes sense if the prefix of sorting criteria, these first n sorting criteria, and the list of sorting criteria attached to distinct on here, if these agree. Only then the whole setup makes sense. Only then we can use distinct on to pick representatives among a group of equivalent rows. And you will also see that without this order by clause attached to the select distinct on query, the query has really questionable semantics. The distinct on here will pick any row, any random row among those rows that are equivalent according to these first E1 to EN. Whether that makes sense is questionable. But so distinct on normally almost always goes together with order by. Okay, so I brought an example. Wait, let's see. I think I brought a slide that explains that graphically. Yeah, wonderful. Okay, so you see that the rows of this table are being partitioned into A1 groups. All rows that agree on their A1 value will form one group. Okay, so these two rows agree on their A1 value. The value is XY, and so they form one group. These three rows form one group because they agree on the A1 value. It's XJ for all of them. Okay, so this is the grouping. Okay, among these groups, pick one representative row. And this is where A2 comes into play, or the second ordering criterion comes into play. In such an A1 group, pick as representative the row with the largest A2 value. In the sort order defined by this particular criterion, the row with the largest A2 value comes first. It will be the representative. So in this table, you can see which row will be picked in this particular group. YI1 will be the largest A2 value in this particular group, so this is the representative. Okay, let me draw that. All right, this representative row picked by the distinct on. Okay, now it's time to switch over to the editor, and you will see that I've brought some of these distinct on queries with me. So let's see. This is the playground table, okay, and we form groups based on the C column. If you recall, the C column is, we see it down here, that's the column that carries Boolean values. If this is the criterion on which we form partitions or groups in this particular table, there will be at most two partitions, the true and the false partition, okay. Inside these partitions, which row is picked? Which row is picked as the representative? And we can see that here, well, it's the row with the smallest TD value. the row with the smallest TD value, because this implicitly means TD ascending. Okay, so the row with the smallest TD value will come first in sort order. It will be the representative of its group. Okay, so we expect 2 rows here. The false and the true representative has been chosen, and it's to be the rows with value D20 and D10. Okay, so let's see whether this actually makes sense, whether this fits the table. Let's order it by TC and TD. Just okay, so this is the false group, and the smallest TD value is 20. We have seen that. This is the true group, and the smallest TD value is 10. We have seen that too. So the Distincton has done its job just fine. Okay. For an experiment here, for a questionable experiment, let's remove the order by clause and then still perform the Distincton. Something will be happening here. Something, 2 rows will be output for the true and the false group, but which representatives will be picked, I don't know. Let's append a semicolon here. Okay, some other rows have been picked, but that's completely arbitrary and could change in the next evaluation of the same query. Do not rely on it. Even if we remove this particular order by query, the internal evaluation of this query will lead PostgreSQL to do some sorting. That's something that some people find puzzling, but it's not puzzling at all. How would you identify the rows in a table that belong to one group? If that table has a really has a significant number of rows, it's a non-trivial task to identify the groups of rows that belong together. And internally, you could do that via hashing, or you can do that via sorting. We could lead PostgreSQL to reveal its internal planning when it forms these groups. Even in the absence of order by, we will probably see a sorting operation. Yes, we will probably see a sorting operation. So the rows of table T are read, all of them are scanned. We then sort by C. The consequence is that all rows that belong into one group, into one partition, will be adjacent to each other. And then we could use a particular operator unique that from these sorted partitions only picks one single row, one arbitrary row in that particular case. But also this group forming is performed by an order by operation. And as I told you, it really doesn't make much sense to have a Distincton clause that performs grouping based on some criterion, column C, for example, but then order the incoming rows by some other criterion, say A. This is something that PostgreSQL will reject for evaluation. And again, the error message here makes sense. The Distincton expressions, the list of Distincton expressions in parentheses, and the order by expressions, they must match. The prefix of the order by must match the Distincton. One final word on the use of distinct in queries. You may have seen other uses of distinct in SQL queries already, and that's the so-called distinct clause. No on here. You see, if this is just a plain distinct clause, no on here. In this case, the semantics of the distinct clause is perform the usual query evaluation operation. So from clause comes first, then select clause comes, and we will see how the resulting rows will look like. And then distinct will remove all duplicate rows. So we will never see duplicate rows in a query that has this distinct modifier attached to the select clause. The result will be a set of rows, not a bag of rows with potential duplicates, but a real set of rows. Any duplicate removed, and all of the k fields, all of the k columns of the resulting rows are being used to decide whether duplicates are present, yes or no. All of these k columns are used. This is different from the Distincton columns, where we could identify the rows that would decide group membership. In this case, all of the k fields are relevant to decide whether two rows are duplicates. Any two rows that differ in only one of these k rows are considered to be unique. Okay, of course we can never rely on row order in such a query. Select distinct internally, as I showed you, is properly evaluated using hashing or ordering. But even if ordering is used in the plan, do not rely on a particular row order in the absence of an order by clause. So select distinct explicitly ask for sets of rows. Sometimes it makes sense for documentation reasons to just replace this distinct by this all modifier. And the all modifier says, yes, I'm aware that the result may contain duplicates, which is the default in SQL, and I'm okay with this. So please application, please user, expect duplicates to be returned from this particular query. As I said, this is the default behavior in SQL and would not need any particular modifier, but this all modifier can be used to explicitly document to the readers of your query, hey, expect duplicates, the result will be a bag of rows. Okay, so much for that. So much for row ordering and the positional row access and what we can do with this based on the distinct keyword. Lots of more to come today, so stay tuned and bye-bye.